Hi there, dear students, and welcome to this comprehensive IGCSE Maths lesson series. So we will be covering both the core and the extended syllabus. And as we go along, I will highlight the extended portions of the syllabus. And if you're only concerned with the core syllabus, you can skip out on it. All right. And if you're interested, you can just like watch it for knowledge and stuff. So the first lesson, we will be reviewing concepts that you're already familiar with, right? So this is just like a quick overview, just to ensure there are no gaps in our knowledge as we take on more advanced topics. So the first one is numbers, right? And we're going to look at the very fundamental of math, the real number system, right? And the number types. So the first one is the natural numbers. So these are the positive numbers, right? One, two, and we're going to put them into these curly brackets. Later on, we're going to learn that this is the sec notation, right? So for now, sec is just a collection of objects enclosed in curly brackets. So one, two, three, and on, all the way to infinity, right? Which is to say that the natural numbers never end; they just keep on going, right? So those are the natural numbers. And if you add on zero to the set of natural numbers, you get the set of whole numbers. So 0, 1, 2, 3, 4, again, all the way to infinity. So this is the set of whole numbers. All right. And the integers are the positive numbers, the negative numbers, and zero. So we have zero in the middle over here, right? And just like the whole numbers, this goes on in one direction until you reach infinity. And we also go in the other direction. So we have -2, -1, -2, -3, all the way to minus infinity, which is to say it keeps on decreasing. The numbers to the left keep on decreasing, right? So that's the set of integers. So we have the natural numbers, the whole numbers, and the integers. All right. Now, those are the basic types, and there are more. Two specifically very important types are the rational and the irrational numbers. But we won't be looking at that now. We will look at that later. All right. So this is the broadest categorization of numbers in terms of rational and irrational numbers. All right. So for now, we are going to look at more basic types. The even number, right? So these are numbers divisible by two, which is to say when you divide them by two, you have no remainder, right? So division works as follows, right? If we have 6 divided by 2, right? And that's 3. So in this case, we say that 2 is the divisor, 6 is the dividend. So this is the dividend, the divisor, and this is the quotient. All right. So for example, if we were dividing 7 by 2, we would have gotten 3, but we would have gotten 1 as remainder, right? So that's the remainder. So that's a very basic concept that you're already familiar with. So numbers that are divisible by 2 are ones when you divide them by 2 have no remainder, zero remainder, right? So for example, 2, 4, 6, 8, these are all even numbers. And for all odd numbers, we have the definition, which is the mirror reflection of the even number definition, not divisible by 2, right? So 3, 5, 7, 9, all these numbers, when you divide them by 2, you have 1 as your remainder. So those are odd numbers. So now we're going to look at an interesting type of numbers, the prime number. But before we get to that, we need to have two definitions in our arsenal. One is the definition of factor, right? And multiple. So this is a very intuitive definition. So, for example, if you have 8, the number 8, its factors are 1, 2, 4, and 8. All right? Yeah. So we have for 8, 1, 2, 4, 8. So we say that these numbers 1, 2, 4, and 8 are factors of 8. So for any given number, its factors are all the numbers that divide the number without leaving any remainder, right? So let's see another example. For example, if we have 9, right? So all the numbers that divide 9 without leaving a remainder are 1, 3, and 9, right? So 1, 3, and 9 are the factors of 9. So as you can see, every number, for any number that you can think of, right? 1 and the number itself are always factors of that number. So we denote this by writing an F with a subscript. So if you want to know the factors of 10, right? We'll write it as follows, and we will say that the factors of 10 are 1, 2, 5, and 10, right? And for multiple, for example, if we had 2, the multiples will be 2, 4, 6, and so on and so forth. So there are an infinite numbers which, when you multiply 2 with a number, you obtain them, right? So there are multiples of 2. So the multiple is the number multiplied with another number, all right? So all the multiples are numbers for which 2 is a factor, right? That's another way of looking at it. So for example, if I were talking about 10, the factors, the multiples of 10. So that will be all the numbers that are divisible by 10, right? So for any number, all the numbers that divide that number, right, are the factors. And all the numbers that the number divides without leaving any remainder are its factors, right? So I hope that division is clear of factor and multiple. So now back to the definition of a prime number. A prime number is any number that has only two factors, which is 1 and the number itself, right? So, for example, 7 is a prime number because 7 is only divisible by 1 and 7, 1 and the number itself. There is no other number that divides 7, right? If you were talking about 8, 8 is not a prime number because it's divisible by 2 and 4, uh, in addition to 1 and 8 itself. So it's not a prime number, all right? So such a number, which is not a prime number, is called a composite number, all right? Composite. So those are two types, the prime number and the composite number. And the square number is pretty straightforward. It's any number which is obtained by squaring a number, right? So 4 is a square number because it's obtained by multiplying 2 with itself. 9 is a square number because it is obtained by 3 multiplied with itself. And 25 is a square number because it's obtained by 5 multiplied by itself. All right. So a quick recap: natural numbers are all the positive numbers from 1 to infinity. Whole numbers are the natural numbers with the zero added to it, right? Integers are all the positive, negative numbers and zero. And even numbers are all numbers that are divisible by 2. Odd numbers are numbers that are not divisible by 2. And prime numbers are numbers that have only two factors, 1 and the number itself. And square numbers are the numbers obtained by multiplying one number with another, right? So there's the definition of factors and multiples, right? So all the numbers that are divisible by any given number are its factors, and all the numbers that the number divides perfectly without leaving any remainder are its multiples. All right, so I hope that's clear. And we have one more definition to look at, that's a fraction. So this is another familiar concept. A fraction is, by definition, part of a whole number. All right. So its general form is A over B, right? Like, for example, if we have 1 divided by 2, which when written in decimals is 0.5. So there are two ways of writing a fraction. It's either what's called as a common fraction or as a decimal, right? They're one and the same thing. So you're already familiar with the decimal system, but we will look at it further uh, in the upcoming lessons. So there you have it. That's the fraction. And then there are the types of fractions, right? Uh, for example, 4 over 3. And yeah, this is the numerator, and this is called the denominator, right? So the fraction in which the numerator is greater than the denominator is called an improper fraction. And the fraction in which the numerator is smaller than the denominator is called a proper fraction, right? So there you have it. That's the definition of a fraction and some of the types of fraction. There's one more type of fraction, the mixed fraction, but we will look at it later. So yeah, that's the basic number types. So for the next topic, let's look at some symbols that is absolutely crucial and fundamental for any student of mathematics to know. And you've already encountered some of them. So this is the equal to sign, right? This is the not equal to sign. So for example, 3 equals 3, right? But 4 is not equal to 3. And this is a symbol for is approximately equal to, right? Like for example, we can say that pi is approximately equal to 3.14. And we will learn much more about pi in the later lessons. So there's the symbol is less than, right? For example, 3 is less than 4. Then there is less than or equal to, right? For example, you can say x is smaller than or equal to 3. So that means all the numbers from uh, 3, 2, and all the smaller numbers, all right? Then this is the symbol for greater than 4 is greater than 3, right? Greater than or equal to, you get the idea. If x is greater than or equal to 3, then we have 1, 2, I'm sorry, 3, 4, and all the numbers greater than that, all right? And then we have the symbol for therefore. This These three dots signify therefore, right? Rather than writing therefore, we use the symbol. And finally, the square root symbol, right? So the square root of 9 is 3. So these are some of the common symbols, and you will repeatedly encounter them, and they will become like uh, really, really obvious as you go along. So now that we have looked at number types and the symbols, let us revisit the ideas of factors and multiples. All right. We've already seen the definition of a multiple. All right. So the multiples of a number or all the number from which that number is a factor. So, for example, if we wanted to know the first three multiples of the number 12, these will be, of course, the number itself, 12, then 24, all right? Then the next number will be 36. So you can think about multiples in terms of multiplication tables, right? So, for example, the multiplication table for 3 is 3 times 1, 3, 3 times 2, 6, 3 times 3, 9, 3 times 4, 12, right? And it keeps on going. So, the multiplication table. So, all of these numbers in the multiplication table for 3 are the multiples of 3, right? You multiply that number with 1, then with 2, then with 3, and all the numbers you obtain are multiples of that number. And as you can see, there are an infinite number of multiples. There aren't an infinite number of factors, but the multiples are infinite. All right. So that's the idea of a multiple revisited. And then we have a very, very important idea related to this concept, the LCM, which is the lowest common multiple. So, as it is suggested by the name, the LCM is the lowest common multiple of a collection of numbers, right? So, it doesn't make sense to talk about the LCM of a singular number. So, you got to have at least two numbers, all right? So, for example, if we wanted to know the LCM of 4 and 7, right? So, what you want is the common multiple of 4 and 7, right? A number for which 4 and 7 are both factors, right? And the lowest number. It's got to be the lowest number for which 4 and 7 are both the factors of that number. So here's a methodology for doing that. The first thing you will do is write out the multiples of the number 4. This is how you represent it. M with the subscript 4. So those will be 4, 8, 12, right? 16, 20, 24, 28. So let's stop at 32 and write out the multiples of 7, which are 7, 14, 21, 28, 35, 42, and so on. Right? So we don't need to go further. We can examine this list of multiples for both numbers, right? And you can find the lowest common number uh, in this list. So upon examination, right, you see that 28, we have 28 over here in the list of multiples for 7, and we have 28 over here in the list of multiples for 4. So this is the lowest number, 28, for which 4 and 7 are both factors, are common factors, right? So these are common factors for 28, 4 and 7. So 28 in this case will be the LCM. So I hope that concept is clear. And next, we're going to revisit the factor, right? So that's simple. Any number that divides a given number is a factor of that number. So for 16, 2, 4, right, 8, these are factors of 16. So the concept associated with factors, right, like the LCM, is the HCF, the highest common factor, right? So what is the HCF, the highest common factor? So once more, this concept doesn't make any sense. All right, if you're talking about a singular number, you've got to have a collection of numbers. Like for example, with LCM, we could have very well asked for the LCM of 4, 7, and 9, right? So you would have had to add a list of the multiples of 9 over here, and then you would have to find out, right, the lowest number for which all three numbers are factors, right? So that would be the LCM in that case. So with the highest common factor, if you are given a pair of numbers, or a collection of two or more numbers, for example, if you want to find the HCF of 8 and 24, right? So this time you're going to write out all the factors of 8, which is pretty straightforward: 1, 2, 4, and 8, right? And all the factors of the number 24, which is 1, 2, 3, 4, 6, 8, 12, and 24. So this time around, you'll have to examine the list and find the highest number in the list. All right. Because this time it's going to be a terminating list, right? It's going to end because factors are limited for any given number. So we can see that in this case, the highest number that appears on both lists, right, is 8. So it's the highest number that appears on both lists. So what that means is that 8 is the highest number that can divide both 8 and 24. Over over here with the LCM, the our LCM was 28. So what that meant was that 28 was the lowest number, uh, which was a multiple of both 4 and 7. So with 8, this is the highest number, which is the multiple, which is the factor for both 8 and 24. So yeah, uh, that's the that's what we have covered so far. So we have the number types, right? We saw the definitions of factors and multiples in order to understand the definition of prime numbers, we saw the common symbols, mathematical symbols that are used in writing out solutions, right? And then we saw the concepts for LCM and HCF, all right? So next up, we're going to look at the concept of prime numbers in a little bit more detail. All right. So we have already seen that prime numbers are numbers that have exactly two factors, one and the number itself. And all the numbers that are not prime numbers, which is to say they have more than two factors, are called composite numbers. All right. So a concept very closely associated uh, with prime numbers is the prime factorization. The prime factorization of any number, which is to say expressing the number as a product of its prime factors, right? So, for example, this would be better illustrated with an example. If we have the number 36, all right, and we want to find the prime factorization of the number 36, here is how we will go about doing it. So, there are two ways of doing this, methods. One method is the factor tree, all right? So, this is how it works. You write out the number 36 like this, right? So, to draw the factor tree of 36, here's what we'll do. We'll draw two branches over here, right? On the first branch, we can write the smallest prime factor of 36, which is 2, right? So we'll write 2 over here and the quotient on the other branch, which will be 18, all right? Then for the second branch, we will again draw two branches over here and repeat the process. So once more, 2 is the smallest common factor, right? The smallest factor, prime factor. And on the other branch, we will write the quotient 9. So this time around, the smallest factor is 3, right? And we have 3 on the other branch. So we keep repeating this process until we have a branch which has only prime factors, right? And then we will circle out all the prime factors. So this tells us that 36 can be written as 2 multiplied by 2 multiplied by 3 multiplied by 3. All right. So this is the prime factorization of 36. Now let's do it for another number, for 48. Again, we draw two branches like this, and we think of the smallest prime factor for 48, which is 2, right? So we have 24 on the other branch. Once more, we have 2 as the smallest prime factor. We have 12 on the other branch. Then we divide by 2 once more, and we have 6. Now, this time around, 2 again is the smallest prime factor. So we circle out all the prime factors and we just multiply them all together. So this gives us 48 equals to 2 multiplied by 2 multiplied by 2 multiplied by 2, 4 times, right? Multiplied by 3. So this is the prime factorization of 48. So that's the first method, right? Factor tree. The second is much more preferable method is by division, right? So once more, let's try and find the prime factorization of 36. So this time around, you're going to divide it by the smallest prime factor, right? And write the quotient over here. And then you divide again by the smallest prime factor and write out the quotient over here like this. Then the next smallest prime factor for 9 will be 3, right? And the quotient is 3. And finally, you keep on repeating this process until you get 1, right? Because when you get 1, the process terminates. And you simply multiply out all these numbers, all these prime factors. So once more, 36 equals 2 multiplied by 2 multiplied by 3 multiplied by 3. And let us quickly carry out a similar evaluation for 48 over here. So we have 48 divided by 2, which is 24. Once again divided by 2, which is 12. Once again divided by 2, which is 6. Once again divided by 2, which is 3. And finally, we divided by 3, which gives us 1. And here the process terminates. So we have 48 equals to 2 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 3, right? So that's how you find the prime factorization of any composite number, right? Because for the prime number, there's no sense in talking about the prime factorization, right? So for example, if you were talking about 7, obviously it can be written as 7 into 1 at most, right? So it doesn't make any sense. So this only makes sense for composite numbers. And now we're going to revisit a concept that we just saw, which is the HCF and the LCM. So a much more elegant and much more broader way of calculating the HCF and LCM of a collection of numbers is through prime factorization. For example, let's look at this question. We have to find the HCF of 168 and 180. So with our previous method, we would have to write out a very long list for all the all the factors of 168 and 180, right? Uh, a much more convenient way is to first express 168 and 180 as prime factors, as a product of prime factors, right? So you have to write out the prime factorization of 168 and 180 uh, first. And that's pretty straightforward. Let's use the division method for 168. So divided by 2, we have 84. Once again, we divide by 2, we have 42, 21. This time around, we're going to divide by 3 so that we have 7, and then we divide by 7. And that's where the process terminates. So that 168 equals 2 multiplied by 2 multiplied by 2 multiplied by 3 multiplied by 7. All right. And moving on to 180, we have 90, 45. We divide this by 3, 15, again divide by 3, 5, again divided by 5, 1. So that 180 equals 2 into 2 into 3 into 3 into 5. All right. So now that we have expressed both the numbers as product of their prime factors, right? So here is how you're going to find the HCF. It's a very straightforward procedure. What you do is you look at the prime factorization, right, and identify the common multiples. So over here we have 2 and 3, right? Because 7 is not a common, my mistake, sorry, common factors, common prime factors. We look at the common prime factors in both the prime factorizations, and we see that they are 2 and 3 because we have 2 in both, right, and 3 in both. And you simply multiply them out, right? So that we have 2, right, that occurs in both prime factorization, and then another 2 that occurs in both prime factorizations, right? Multiplied by 3, which occurs in both prime factorizations, so that we have 12. So 12 is the highest common factor, the HCF, for 168 and 180, right? So it's a fairly straightforward procedure. You write out the prime factorization of all the numbers involved, and then you look at those prime factorizations and identify the common prime factors, and then just multiply them all out, and that will give you the HCF, right? So what about the LCM? So for example, if we wanted to find the LCM of 72 and 120, We have to find the LCM, the lowest common multiple. Again, we're going to write out the prime factorizations of 72 and 120, which are 72 divided by 2, which is 36, divided by 2, which is 18, divided by 2, which is 9, divided by 3, which is 3, and again divided by 3, so which gives us 1. So that means 72 can be written as 2 multiplied by 2, multiplied by 2, multiplied by 3, and then again multiplied by 3. And what about 120? So let's divide by 2. So we have 60, we again divide by 2, we have 30, we again divide by 2, we have 15, we again divide by 3, 5, again divide by 5, 1. So that 120 equals 2 multiplied by 2, multiplied by 2, multiplied by 3, multiplied by 5. All right. So now this time around, what we're going to do is we're going to look at both the prime factorizations, right? And we're going to identify the common factors, common prime factors. So we have 2 over here, right? And 3. And then we're going to include the largest power, right? Which means the largest set of the common factors, right? So 2 is a common factor in both, and its largest set is 2 into 2 into 2, right? So we're going to write out the LCM as 2 multiplied by 2 multiplied by 2, right? That's apparent because 2 occurs in the same set in both numbers, in the prime factorization of both numbers. But what about 3? In 120, 3 occurs only once. But in 72, it occurs twice. And we are going to choose the larger of the two sets, which is 3 by 3. So 3 by 3 goes over here, right? And finally, we're also going to look at the prime factors which are not common. In this case, 5. And we're going to multiply it out into the expression, right? So this will equal 360. So 360 is the LCM. All right. So let's recapitulate the HCF and the LCM. We first write out the prime factorization of all the involved numbers, right? And for HCF, you look at the common prime factors and multiply them all out together, right? But with LCM, you not only do you identify the common prime factors, but you choose the largest set in which they occur in either of the two numbers, and then you multiply them all out, and then you multiply also the uncommon prime factors found in either of the two numbers, and then multiply them here as well. So that gives you the LCM. So yeah, thank you so much. This was the first lesson. In the next lesson, we'll continue our study of numbers, and hopefully, in the next lesson, we will be done with our revision of numbers. Right, all this basic stuff. Again, you probably know all of this, but it doesn't hurt to ensure that there are no gaps in our knowledge as we proceed with more advanced topics. So, thank you very much. See you in the next lesson.